Okay, so today's session we're going to spend a little more time on polar. I wish we had more time in the course because I could spend literally weeks on this interesting subject. But we're just dipping into it a little bit. In second year calculus, you actually will do quite a bit with this. It's very, very practical for many reasons, and I'll try to point that out with a couple examples today. Anyway, so we're going to start out with that today, polar equations and graphs, and then I hope I have enough time to at least introduce the topic of vectors, which again is another very important topic used in physics, engineering extensively, and video games and all that kind of thing. So we want to make sure we touch on those subjects. What I want to start with, though, is we had a problem yesterday. We had a rain gutter in the last session where we bent up the edges and we formed a gutter, and we were looking for what angle do you bend those edges up to form the maximum cross-sectional area. And the equation that I came up with in class to describe that area was not right. And we saw that it wasn't right when we compared it with what the book had and then also our general thinking. So take a look at this write-up here that I did. Here's a picture of that problem where we folded up the edges, and I can point out to you fairly quickly here where the error was in the equation. So the approach we took yesterday is we took the general equation for the area of a trapezoid. And is that large enough for you guys for video recording? Okay, thanks. So here's the general area equation, and we took the height of this trapezoid, which is 4 sine theta, divided by 2, times the sum of the legs. Now here's where the mistake was yesterday. We took this leg 4, and then we needed to add this entire leg up here, and what I forgot to do was to add the 4 again up there. I did include the 4 cosine theta, and twice we have 2 of those pieces here and over here, and that's right here, 2 of the 4 cosine theta pieces, plus the other piece on the top, plus the bottom. And that's where the mistake was. Here's the equation right here. You factor out the common 8, and you get the equation that agrees with what the authors had. Now, here's another way of thinking of that. Because this is a nice regular shaped trapezoid with symmetry, if you took this left-hand piece over here, notice that the lower edge is parallel to the upper edge, and so therefore with this transverse coming through here, these angles, theta here, is the same as the angle up here. So that means this triangle, if we cut this triangle off and glued it on over here, we would form a rectangle shown right down here. The area of that rectangle is base times height. Here's your base, here's your height, and that equation is exactly the same as the equation we got using the other formula. Okay, now I prepared a handout, and what I'm going to do is I'm not going to spend time today because I want to go back to polar with you right away. But what I want to do is I want to shift this up a little bit so we can see this on the recording. Is if we then graph this area function as a function of angle theta, and I went ahead and did the mathematics, or did the graph, all the way out to 180 degrees. What happens when you draw this graph, only a portion of this graph is going to be reasonable, because keep in mind, we're letting this angle theta up here, we're letting this angle theta up here change. And we know that that thing physically for the gutter, we don't want that probably to go any higher than 90 degrees. If it goes higher than 90 degrees, then these outer edges would start to fold in, and eventually it would form, let me show you down here. If you folded that 4-inch piece past 90 degrees, it's going to fold in, eventually forming a closed rain gutter, which isn't going to do any good practically, but it would form an equilateral triangle. The area of that equilateral triangle you can figure out easily by base times height divided by 2, and that turns out to be equal to a value shown over here. So the equation that we graphed actually mathematically will work and physically will work all the way to 120 degrees. The problem that was posed in the book was to find the maximum area and what angle you would have to use to obtain that, and that would occur at 60 degrees precisely. I have a handout prepared for you folks, and those who go on into calculus, you will learn how to take a function such as this one right here for the area and find what's called its derivative. Another word for it is you can think of it as a slope function. It's the rate of change that you see. In other words, you can see the way the slopes change as you lay a ruler up against the edge of this curve, and right up here at the top, the slope would be 0. You're going to learn in first term calculus the following: how to find what's called the first derivative. I have a handout for you on this. You will find this first derivative. You will work out the math and look at the trigonometry in here. This thing cleans up. See this? Cosine squared minus sine squared. That is cosine of twice theta. So I took this term, 16 cosine twice theta, put it first, followed by adding 16 cosine theta. And then we want this slope function here to equal 0, so that we're going to be up here at the top where that slope is 0 there. And then solving this trig equation, look at the mathematics here. Use your trig identity on the double angle formula. You need to turn this all into a cosine structure. I'm just going through this pretty quickly, obviously. And so we're working on solving this equation. We replace the sine squared with the Pythagorean identity, 1 minus cosine squared. Clean this up, and look what happens. It turns it into a quadratic function in terms of the cosine. That happens to be factorable. This right-hand factor equaling 0 yields -1, but that gives you an angle of 180 degrees, which makes no physical sense. The other factor over here, the cosine value equaling this factor equaling 0, yields cosine theta equals 1/2. The angle, 60 degrees. Okay, so very nice calculation. At 60 degrees, you plug this back into your area formula here, shown on the bottom. Clean it up with a little practice from intermediate algebra. And here's the exact answer, 12 square root of 3 square inches, approximately 20.78, which, up at the top here, matches the value off the curve. Okay, I have a handout for you on that, and we've got it here on the recording. You can hang on to that handout and use it. Go pull it out when you're in first term calculus, and you'll find it useful. Okay. Now, back to polar. Oh, just quick comment for the class. Test next Tuesday in the Math Resource Center, or in the math lab upstairs, the computer lab upstairs next Tuesday. And bring your homework folder up through 8.5, which was the simple harmonic motion problems. Okay, let's have some fun. There are a multitude of polar functions that we could graph. And what we want to do is I want to have you get in the habit of not just relying on your calculator to obtain these graphs and understand it, but to actually try to be able to do it by hand with pencil and paper. So here's a polar function. This happens to be a question out of the book, number 52 on page 587. Here's the polar function. The radius is equal to 3 times the cosine of 4 theta. And the habit I'd like you to get into is, if this function is simple enough, which this one is identify the period. The period of this cosine function is going to be your normal 360 degrees divided by what? Divided by 4, right? And 360 divided by 4, you know, is 90 degrees. So this cosine function here is going to go through a complete cycle in just 90 degrees. It's been squeezed in by a factor of 4. So what I'm going to do is I'm going to draw what I like to call the rectangular plot. And here it is, and I'm going to draw it large enough that I can do several cycles. So I'm just going to be drawing several cycles of cosine. 1 cycle, 2 cycles, 3 cycles. And it could keep on going for theta. So there's 3 cycles. Now we know 1 cycle is 90 degrees. Another whole cycle would put us at 180 degrees. A third cycle would get us to 270 degrees. Feeling good? And then for plotting these other points, we need to take the period, which is 90 degrees, and divide it into 4. Well, that's going to be chunks of angles of 22.5 degrees, 22.5 degrees, 45 degrees, 67.5 degrees. Check my arithmetic. 90 degrees, 112.5 degrees. I actually wrote notes down, except I can't read them. I think that's right. And then if I add 22.5 to that, I should get 135 degrees. Add another 22.5 to that. I need these angles. These are important. And then if I add 22.5 to that, I get 157.5 degrees. If I add 22.5 to that, I get 180. So I'm feeling good. Right? And what's the maximum radius? Look at the equation. What's the maximum value of the radius? 3. Because cosine, we keep saying, can't get any bigger than 1. So the maximum radius here happens to be 3, and the radius also can be negative. Now, in the last session, we talked about the fact that, here's my arm again, we're going to set an angle, and the positive direction for the radius is out along that line, once you set the angle. Out along that line. Where's the camera? There. Out along that line is positive. If the radius happens to be negative, like you see in some of these regions here, then your radius actually is going to be plotted back the other direction along that line. Back the other direction along that line. So I'm going to need to draw, I want to get to the polar plot. That's our objective. So what I need to draw is lines that are going to be at these different angles, because these are the angles that are going to be kind of critical in doing the drawing for the polar graph. You're going to love this picture. This is exciting. And it's almost springtime, isn't it? What happens in the spring? The flowers start to blossom, right? Okay, watch. Here we go. So we're aiming towards trying to generate a polar plot. A polar plot. Notice, isn't there some symmetry here? Even if I went negative on this, right? Isn't there symmetry around 0 degrees? And around 45 degrees? And around 90 degrees? Etc. Right? Do you see the symmetry of the function? What's going to happen whenever you see that, that's going to show up as symmetry in the polar graph. So over here for the polar plot, I'm going to take and draw lines dotted at 45 degrees, because I'm pretty good at that. And then I'm going to split each of those in half to be able to get on the 22.5 degree cycles. 22.5 degrees right there. And that comes back down negative over this way. Whoops, that's not looking too good. Might as well try to make it decent here. I split this up. That looks pretty good. And then when I get to, what, 67.5, coming down through there, like this, 90 degrees there. And then beyond 90, whatever that was, 112.5. And you can see why that little sample polar graph paper piece I gave you yesterday could be useful. And I also showed it in the recording. And then past 135 degrees, we've got another one here. So you can see I've got drawn now a bunch of axes, polar axes, or lines, that are at these different angles. So this is at 22.5 degrees, at 45 degrees, 67.5 degrees, 90 degrees, 112.5 degrees, 135 degrees, 157.5 degrees, 180 degrees, etc. Okay. Now, here's where we have the fun. Ready? At 0 degrees, let's work our way around the room. At 0 degrees, what's the radius, Steve?
At 0.
At 0 degrees, what's the radius?
1.
Hold it. Look at this function. 3, right? It's been amplified at 0 degrees. Matter of fact, you could even put it in here. You could build a table of theta and r and just go to your function and build that table of values, okay? At 0 degrees, you're at 3. Okay? At 0 degrees, you're at 3 right here. You come over to the polar plot. What are you going to do, Tom?
I'll go to 3 and make a take 1.
Okay, I set 0 degrees. Positive r is that direction, right? And I count out 3. 1, 2, oops, let me make it decent here. 1, 2, 3, right? There's a point. 3 at 0 degrees. Feeling good? Okay, now, look back over here at the rectangular plot. What's the radius doing as I move from 0 towards 22.5 degrees? What's happening to the radius? The radius is decreasing, isn't it? As I move towards 22.5 degrees, until when I get to 22.5 degrees, the radius is 0. So watch what happens. Imagine you've got a bracelet on, like I said yesterday, right? So here's my arm, which is going to sweep with the angles, and my bracelet's out here at 3, and then what happens as I move towards 22.5 degrees, the bracelet slipped up my arm back here to the pole. So the graph, as I let the angle sweep towards 22.5 degrees, the radius from the pole, that distance keeps getting shorter and shorter and shorter. And so the graph comes in nice and smooth. Look at this. The reason I drew this 22.5 degree line is because the radius comes in just tangent to that, just touching that line. Doesn't sweep over that line, because otherwise the angle, if you swept those radiuses over that line, you'd be past 22.5 degrees. So the graph comes in this way, folks. See the arrow? And let's label that with a Roman numeral 1. That behavior is going to relate to this little segment of this rectangular plot over here. Now here's where it gets pretty cool. Let's go past 22.5 degrees. We're going to be letting our positive r be sweeping, or our angle is going to be sweeping. Positive r is going to be pointing out that way, isn't it? As I head towards 45 degrees. Matter of fact, it's always going to be the positive r, as I let these angles sweep, is always going to be pointing out radially from the pole. The negative readings would be back down in the opposite quadrants. Come back here. When you go between 22.5 degrees all the way up here to 67.5 degrees, the radius readings are negative. So this behavior we just did here is going to show up in similar fashion here, isn't it, in value? except the values are going to be we're reading negative radiuses. So as you move from 22.5 degrees towards 45 degrees, the radiuses are going to actually be plotted back down in this segment down in here. Because when you're at 45 degrees, your positive R is pointing out there. The negative R readings are back down this way. And so we come off this tangency right here on this 22.5 degree line. We're going to come off that tangency, and the radiuses are going to grow out to a -3, aren't they? -1, -2, -3. So the radiuses are going to sweep out that way until we get to this point, and this happens to be an R reading of -3 when you're at 45 degrees. Right there.